Hey guys, and in this long overdue statistics video, we're going to talk about a really cool way to get around assumptions of statistical tests called doing a randomization test. So if you've watched any of my videos, or indeed you know anything about the null hypothesis significance testing approach, you know that statistical tests make certain assumptions, and if those assumptions are met, the results we get from the test are often biased, and we can't use them to make inferences about our data. A lot of people have come up with lots of suggestions for this, and previously I've gone into some of the solutions. Mostly revolve around transforming data, but that doesn't work very well because it often transforms the data into a different space, so makes interpretation more difficult, and it often doesn't work anyway, doesn't help to satisfy the assumptions. So there are other things we can do, one of which is called a randomization test. First we're going to talk about the logic, and then we're going to get into what it is. So to understand the logic of a randomization test, we first need to understand null hypothesis significance testing itself. So when we get a test statistic from a statistical test, be it a t-test, an f-test, or whatever, what we're actually doing is testing that test statistic against a sampling distribution of test statistics that would be likely to occur under the null hypothesis, and seeing, okay, what's the probability, looking at distribution, of us getting the score that we got, or a more extreme score, if the null hypothesis were true. And that's what statistics is based on. But those probability distributions, sampling distributions that we can compare our test statistic to, have been derived theoretically, and because they're difficult to derive, certain assumptions had to be made when they were done. Otherwise, it would just be too difficult. So that's where the assumptions come from. And if we don't make those assumptions, that's why we then can't trust the p-values. But a randomization test basically says, why can't we use our own data to create the sampling distribution and set up situations where our the null hypothesis is guaranteed to be true, and try out those different situations, and compare that situation to the statistic we did get, and see if it's more extreme than that distribution that we've derived from our own data. As well as sorting out assumptions, this can also be useful when we have data that or something we want to test for which the sampling distribution hasn't been theoretically derived. So that's the theory. For the rest of the video, we're going to look at how to actually do it in R. So let's dive in. I've got R open here, and let's open our example, which is in a data frame called full DF. So here we've got several executive functioning measures completed by 55 participants, and basically the idea is that we've got this general measure of executive functioning that we've developed, and we want to see how well it correlates with 9 classic measures of executive functioning. But because there are 9 tests, we don't want to do 9 correlations, because that's too many statistical tests, and that's going to give us very low power. So what we want to do is calculate the mean of those classic measures, and see what the correlation of our new measure is with the mean of all the other scores. But we can't do that because there isn't or the sampling distribution for what something looks like compared to the mean of several other items hasn't been derived, so we can do it empirically. So let us look at the R script we're going to be using to do that. I've got it open here in just a text editor. So because we've got our original values here. First thing we're going to do is generate a new column, which is the $, which is just going to calculate the mean for each row, so the mean for each participant of column 2 to column 10, which are our classic executive functioning measures, column 2 to column 10. Once we've got those, we're going to say we want to keep all the rows, so we're leaving this here, but we only want to keep column 1 and column 10, because we can get rid of all these classic measures now that we've calculated the mean, which we actually want to use. And then this is the meat of the resampling area. We're going to say loop through this code 5,000 times, because we want to create a sampling distribution, and there needs to be some random element of it that can occur over multiple times. So which is 5,000 here. People choose different values. The specific value you choose generally doesn't matter that much, but the more resamples you run, the more precise your p-value will be. So every time we do this, what we do is create a random sample variable, which we take a sample of the first, or in this case, all the values in the second column of our data frame. Why the second column? Well, remember we've got the GEF measure, and next to it the mean of all the other measures. If we shuffle the mean, which is what this sample function does, just shuffles the items. Well, the correlation between the mean of a shuffled item and the new item itself should on balance be 0 and just differ by random sampling variation. So every time we take a sample, we're then gonna add another. We're gonna work out the correlation of that and add another column to our null distribution. This means I is the iteration in this for loop. So every time it iterates, we're just going to add another value, and we're going to do that 5,000 times. So there should be 5,000 values. We're then going to work out the correlation for the real value. So take what all of the first column of the data frame and correlate it with all of the second column. So then we've got the actual value, and then to work out the probability value under our permutation test, what we're going to do is we're going to print the number, so it's this length function of the amount of values in the null distribution that are more extreme or equal to our real value, and then we're going to get that number, and because we've done 5,000 permutations, we're going to divide it by 5,000. One thing that I forgot to mention is when we do permutation tests, or randomization tests, we sample from the distribution, so we shuffle without replacements. That's not that's the difference between randomization and something called bootstrapping, which I might do a video on in the future. But if we run this code, so I'm gonna actually copy and paste it into our it's gonna throw us some errors, so let's because we haven't previously defined what the null distribution is, we need to basically tell it what that name is. So before it creates any values, we're just going to say null d equals null, just so that it knows what it is. I'm just going to set it to an empty vector actually, and then if we rerun the code, we should get a p-value, so we know that the probability of observing a correlation between the mean and the individual score of that extreme or more extreme is 0.2, so we know that's not a significant result. So for that measure, it doesn't correlate significantly with the mean of our other measures. So that's how to do a permutation test. So yes, the logic is whatever you want to permute, we're just gonna work out what situation would create the null hypothesis. So in this case, I knew that shuffling the items so that the item in one row had no correspondence with the item in the next column would create the situation, the null hypothesis. So I just repeated that 5,000 times, added them all together, and then saw how many times the real value was equal to or more extreme than the values we would have got under the null hypothesis, and it was more than 0.005, so that's not a significant result. One thing to bear in mind is this is for a one-tailed test, because I'm saying more extreme or equal to. If we wanted to do a two-tailed test, we would also have to have one for less extreme, which is a little more complicated. The reason why I didn't do that here is because we have a hypothesis of a positive correlation, so it should be more than or equal to rather than less than or equal to. If you want to do a two-tailed test, you have to work out the p-value for both tails and then sum them together. But anyway, so that was a basic explanation and demonstration of how to do permutation tests. I hope you found that useful, and thank you for watching, and I'll see you in the next video. Bye bye.